Well, good evening. We got the universe in place. Now we need a place for us to live, but then already got us living well before we got the universe in place, which is not the normal way we do this. But at any rate, tonight I want to talk about the origin of the solar system and some of the interesting peculiarities of our particular planet in the solar system and so on. So here is our solar system, and you can see that it has how many planets? There's only 8 planets. Pluto was demoted a couple of decades ago, and in my opinion, never should have been considered a planet. It doesn't fit either category. There's 2 categories of these 8 planets. The inner ones, which are what? Starting from the sun out, what are they? Name them. Mercury, Venus, Earth, and Mars. Their composition is all pretty similar. They are rocky bodies, solid rocky bodies. Venus has a horrendous atmosphere. Earth has just the right atmosphere, thankfully. Mars has very little atmosphere, and Venus none. Excuse me, Mercury none. Venus has a very heavy atmosphere, and because of that, there's a runaway greenhouse effect on Venus, so that the temperature at the surface of Venus is about 900 degrees Fahrenheit, and the Soviets landed 2 craft on Venus, which managed to send data back for a few minutes before they were destroyed. It's not only very hot, it's very, pressure there would be extremely high as well. And the atmosphere has sulfuric acid. Not a hospitable place. Then the outer 4 planets are, go on. Be careful how you say this one. Uranus and Neptune. These planets are all large and mostly gaseous. Now, a couple of interesting things. You notice everybody knows Saturn has rings. Did you all know all 4 of them have rings? Yes, they all have rings, very thin. Well, Jupiter's, Uranus, Neptune rings were all discovered in my lifetime. Of course, Galileo saw Saturn's telescope. What do you know about Uranus? What do you know about Uranus? Yes, Uranus is a lazy fellow. He's kind of laying on his side. And we're going to talk about how the solar system was formed. And any theory that would properly describe how the solar system was formed has to take into account the regularities as well as the irregularities and the extreme tilt of Uranus's axis of rotation is one of those things that we'll have to explain. Before I leave the ring business, the rings are formed by the tidal effects of the massive planets pulling apart moons that get just too close. It breaks them apart and then ends up spreading the particles of that moon all around the planet in a ring. Another peculiar rotation is Venus's. Venus rotates backwards. All the planets, well, of course, Uranus is actually tipped over a little more than 90 degrees, so we call it rotation retrograde, backwards. Venus's rotation is pretty vertical, but it's rotated backwards. Very slowly. A day on Venus is longer than a year. because of its slow backward rotation. So, what else do you see here that's in our solar system? There are asteroids. There's only one asteroid belt. Does anybody know what this outer group of debris is called? Kuiper belt. K-U-I-P-E-R, Kuiper belt. And the composition of the Kuiper belt objects is mostly icy. And that's where Pluto is now designated as one of the Kuiper belt objects. We'll get to that. We'll talk about some of the details there later. The asteroid belt between Mars and Jupiter, those are rocky bodies. There are ice in them, but not like the outer ones. What else do we have in our solar system? Okay, you want to explain the Oort cloud? All right. Most of the comments will come from the Oort cloud. The Oort cloud, the Kuiper belt is a ring of debris, like the asteroid. The Oort cloud is farther out and is more spherically distributed. Probably leftovers from the very early formation of our solar system. Thank you. That's not shown here, by the way. There is something else shown here. It's kind of big. There is a star called the sun, around which other things are revolving. And what about those little things in the upper right corner? Those are comets. Right. Now, there are asteroids that are not in the asteroid belt. We're not going to go into that. But most of them are in the asteroid belt between Mars and Jupiter. It's fewer put them all together. You don't have a very high planet anyway. All of them were put together in one body. But this is one that just never quite formed. Yes. Well, it's not scale. Not at all scale. But it's pretty. Illustrate. And it does what I wanted to do. Okay, so the 8 planets, the sun, a star, and the asteroids, the Kuiper belt objects, the Oort cloud objects, and the comets, which is primarily where the comets do come from. Their orbits, they're highly eccentric, bring them in past the sun periodically. Every time they come in and go near the sun, a little bit of that gets blown off. All right. So on to any model that we would have to explain the origin of the solar system has to explain several things. And I've listed them here. First of all, the planets are relatively isolated in space. Okay, none of the planets are fighting for space. They're well spaced out. And the further out the Jovian planets are really spaced out. Past from Mars out, they're really spaced out. They're nearly circular in their orbits. Their orbits are nearly circular, but not exactly. I think I told you Whipple discovered that the orbits were elliptical because he was using data provided from Ptolemy. Tycho Brahe, Tycho Brahe had data that kept the views. And fortunately, he had most data about Mars. Mars' orbit is one of the most elliptical. And never figured out that the orbit was elliptical. And the planetary orbits all lie in nearly the same plane, not exactly. And the direction of the orbital motion is the same as the direction of the sun's rotation. So everything is going generally in the same direction. The sun's rotating, planets are going in the same direction around that. And the direction of most of the planet's rotation is also the same as the sun's, or we talked about exceptions. Venus and Uranus. And so the theory is going to have to be able to explain these as well as why Venus and Uranus aren't like that.
The asteroids on roughly the same spot. I guess we're not here. I thought that was just. Wonder if the asteroids are the same plane.
They are. So roughly the same plane.
Can you hear me?
Orbit their planets in the same sense. They orbit around the equator of the planet, basically, including Uranus, which is tipped over. The solar system is highly differentiated. Any idea why I mean by that? We're not talking about differential calculus here.
Gas, massive.
All right. As I alluded to, the composition of the parts of the solar system are different as you move from near the sun further out. Asteroids are very old, and they're not like either the inner or the outer planets. That's why it's kind of like helpful to get stuff from these asteroids, and they have been able to bring back asteroid material from some of the more recent efforts. Then there's the Kuiper Belt, which are asteroid-sized icy bodies beyond the orbit of Neptune. And then the Oort cloud, and it's simply the Kuiper Belt, but its composition, belt in the composition is further out, and it's more spiritually distributed rather than in a ring. And the orbits of those objects are therefore random. Since they aren't all laying in the same plane, their orbits are randomly oriented. So the condensation theory, I'm going to skip over the historical development. Actually, there was a back in the 60s, 70s, an explanation that failed a little bit, but it's basically the same idea. Now we call it condensation theory. And the solar system in this theory starts out as a swirling cloud of gas and dust, which as gravity pulls the material toward the center, and it spins faster and faster. What's going to happen to this amorphous cloud of material? It spins faster and faster. Flatten out into a disk. And so these are depictions of the various stages of this process. And this explains it a little further. There's a large interstellar cloud of gas and dust that starts to contract, heating as it does so. Gravitational energy gets converted into thermal energy, and you have a star born. The sun is born from the center, thus provides condensation nuclei around which planets form. And that's the key to this theory compared to one that was proposed much earlier. Namely, that there are condensation centers, little dust particles that provide a surface on which other particles condense. They start holding together. And as the planets grow, they sweep up smaller debris that's near them, and so the planets grow from these. This depicts it pretty well. Early on, there would be a whole lot of debris running around and colliding. That's why the moon, incidentally, has a whole lot of impact craters. The Earth would have had just as many, but because of erosion, we don't notice them as much. But over time, these smaller planetesimals start colliding with each other and joining with each other, and eventually you get a planetary system orbiting around the central star. as I've invited before, anytime you want to ask a question, please feel free to do so. I will make something. So the solar system is evidently not a random assemblage, but it's a single event that produces the solar system. Wasn't it? The sun was formed here, this planet here, and they all just happened to get together. That's not the way it was. Single event. Planetary condensation theory does seem to work well to explain it. And there's lots of room for variation for the irregularities, such as Uranus's axial tilt, Venus's retrograde rotation, and so on. They have to be allowed by this model. And of course, when you think about all these particles running around running into each other, some of these collisions could knock Uranus over on its side, could actually hit Venus in such a way as to make it to start to rotate backwards. So it does allow for these peculiarities as well as the regularities. Initially, dust grains and gases would have been uniformly spread throughout this cloud. But as the center heated up, the heat from the proto-sun, we'll say it's not yet a sun, but the heat from the proto-sun would break those dust particles apart. So in the inner solar system, the dust particles get broken apart. In the outer solar system, they do not, because it's still cool enough that far out. And so after some time, the inner solar system radiated away the excess heat and did cool down. The dust particles were able to reform and start producing planetesimals, which eventually collided and formed planets. Exactly what kinds of material could condense was temperature dependent. And we'll look at that in more detail in a moment. In the innermost regions, only metallic grains could be condensed. About 1 astronomical unit, rocky silicate grains could form. I need a question here. Somebody got a question?
What's an astronomical?
Thank you. What is an astronomical unit? We use that. That's the average distance between the sun and the Earth, and we use that as a measuring rod within our solar system. Like we use the measuring unit of a light year for things beyond our solar system. We need a big ruler, and so we use an astronomical unit, which is how many miles, roughly? 93 million miles. Isn't that about the average distance between the Earth and the sun? Or 8 light minutes. And beyond 3 to 4 astronomical units, various ices could form. Beyond about 5 astronomical units, the temperature was low enough for the various gases to condense into solid form. The gases being mostly hydrogen and helium. Remember, that's the main constituent of that was produced in the Big Bang. But beyond that, we have carbon, oxygen, and nitrogen, which are the basis for the compounds which we find that are abundant in the outer solar system, namely water, methane, and ammonia. The Jovian planets are hydrogen, helium, methane, and ammonia. In fact, it's the methane that gives Uranus and Jupiter its bluish tint. So this slide shows pretty well the idea that I'm trying to make. So this is a graph of temperature on the y-axis and distance from the sun on the x-axis measured in astronomical units. And you can see where Earth, Jupiter, Saturn, and Uranus are located. And of course, Earth is 1 astronomical unit, but Mercury and Venus are with less than 1, and Mars was left out here. But anyway, you can see that in the inner part of the solar system, metals can form, then silicates and rocky materials form at roughly the distance of the Earth. Water ice can form out there at the distance of Jupiter and beyond, and ammonia at about Saturn and beyond. And so that would explain why the solar system is highly differentiated. It's the heat of the inner solar system does not allow for those things to form. You'll notice where water ice forms, or water ice, well beyond Earth. So we have no water on Earth yet. As a consequence of the greater abundance of materials that were available out in the outer part of the solar system, plus they were able to start forming right away because the condensation nuclei, the dust particles, never broke up. So these planets were formed, started forming sooner, and they had more materials because there are more things that could condense out there, including the metals and the silicates could form out there, as well as the ices. And so that explains why the outer planets, which are mostly gaseous, are so much bigger. They have a lot more time and a lot more material to use in their formation. Yes.
Why do you call the outer planets Jovian?
Jupiter becomes the primary one. The inner ones are called, come on now. It's from Earth.
Well, for Jupiter, so Jupiter was a Roman god. He went by the name Jove as well. And so that's why from Jupiter on up, it's Jovian.
Yeah. And the inner ones are called terrestrial, as in terra. And by the way, Pluto was neither rocky nor gaseous. It was ice. It is ice, which is more like the Kuiper Belt objects. So that's why I say it never should have been included as a planet. Though its discovery story is very interesting, which you're not going to get to hear. So the icy planetesimals that were far from the sun were ejected into distant orbits by gravitational interaction with the Jovian planets into the Kuiper Belt and into the Oort cloud. Some were left with extremely eccentric orbits that appeared in the inner solar system as comets. Now this illustrates two things here. You'll notice that some of these planetesimals were deflected by the Jovian planets inward. Most were deflected outward. And this inward deflection is very important. Because what did I say the Earth didn't have yet? Water. Where did we get our water? We got our water from these icy planetesimals that were deflected inward, colliding with Earth, came our water.
So create an atmosphere then too. When the atmosphere was created.
Well, that would have been part of it, but no, we were able to retain some gases because we were far enough away. Venus retained a lot of gases.
I think water is not possible without the atmosphere, right?
True. Yeah, that's why any water on Mars would have escaped long ago. Not enough atmosphere. By the way, Mars's atmosphere is Venus's atmosphere is heavily carbon dioxide. And that's why they were trying not to put too much carbon dioxide in our atmosphere. So we also don't have that runaway greenhouse effect. Mars's atmosphere is 95% carbon dioxide. But it's very thin. It's a very thin atmosphere. Very different from Venus. So let's talk about Earth, which is our home. The Earth formed in the solar system in just the right place. The Goldilocks zone. There's a narrow region around the star where the temperature is just right for life to exist. This is called the habitable zone. Anything formed closer, anything formed further away will not provide habitation for life. And the sun is just the right kind of star. There are lots of stars out there, and they aren't all alike. Our sun is a very mediocre star, but it's just right. Some stars are much smaller and have less gravity. They are reddish in color because they don't get as hot as our sun. And they could not support a planet with life. Some stars are bigger and more massive than our sun and burn much hotter. They would have a habitable zone, but it'd have to be further away. And then stars go through a life cycle. And so our star, the sun, is right in the middle of its life cycle, which is ideal for life. It's been around, we think, for about 5 billion years, and it's only got 5 billion more to go, but don't worry, we're here. But we got just the right kind of star. And if you look carefully at some of the stars out there, you can see the different colors. There are also red giant stars, which are stars that are in the process of blowing off their outer atmospheres. Our sun will do that eventually. Now, let me say a word or two about that. Maybe 5 words or more. There's a balance in the center of a star between gravity trying to squeeze it together and energy produced by nuclear fusion trying to push it out. That balance is maintained in a stable star until there's no longer stuff left to fuse, and gravity always wins. And when the core collapses, the heat generated from the collapse will expand to the outer parts of the star, and the star will begin to expand. There will be a time when our sun will be a red giant and Earth will be orbiting inside the outer part of the sun. That's 5 billion years away. If there's enough mass in that center, it will collapse catastrophically and blow it apart. That's what we call a nova. When you suddenly see a new star erupt in the sky, which you probably never witnessed, but that's called a nova, a supernova. Anyway, stars go through a life cycle. Ours is in the middle of its life cycle, and it's just the right kind of star. The other planets, especially the large ones and our large moon, are also important for our existence. I guess I need to explain that a little bit more. Now, come on, back here. Well, there was this early period when there was a whole lot of debris flying around. It's called the period of heavy bombardment. And as I said, you look at the moon, you can see results of that heavy bombardment. By the way, the far side of the moon, which they just went around and took pictures, looks very different from the near side. It has a lot more craters. The near side has these relatively flat areas called mare, which is Latin for seas or oceans, because when Galileo looked at it, he thought those were bodies of water. But it's actually just lava flow that came out of the moon during this period of heavy bombardment and overflowed the most of the craters. So our moon protects us by taking the hits for us a lot of the time. So do the Jovian planets. With their much greater gravity, anything coming in is more likely going to be attracted to them than to us. Now, you know, we've had a few heavy bombs. We've been hit pretty hard a couple of times in the past. And there are some very large craters. There's one that's not that large. My wife and I have been there. Have any of you been to the meteor crater in Arizona? Been there? Yes. Well, it's very interesting. Nice meteor crater off there in the desert. It's just a few miles off of Interstate 40 in Arizona, between Flagstaff and Winslow, Arizona. Encourage you to visit there. It is on private land. You will have to pay to go in. But anyway, you know, you've heard about the extinction of the dinosaurs, where we were hit by something really big. And the crater for that seems to be in the area of the Yucatan Peninsula. But there are several other large craters on the Earth. But by and large, the period of heavy bombardment finished. We don't get hit very much now. We have PHAs, potentially hazardous asteroids. Some of them come fairly close to Earth, and there's still a chance we will get hit hard again.
Lord,
Yes.
some or all of these possible collision bodies are under observation.
Yes.
But are they all?
No. We keep finding more.
So is it then possible theoretically that you could just out of the blue get hit?
No, they would detect it before it was going to hit us.
But they might have known for 3 days or so.
Yeah, you would have to
Pretty
look.
short notice. I mean,
Yeah, we wouldn't have a whole lot of chance to do anything about it, but but yes, they will know, they will discover. If it's big enough to do us that much harm, it will be detected well before it gets here.
Actually, a comet you can see at the horizon near sunrise right now until 15.
Have you seen it?
I have not.
Yeah.
Near sunrise, you said?
Mhm.
So here we see the habitable zone on this plot of mass of the star versus distance away from the star in astronomical units. And you can see our solar system is portrayed here. There's our sun at 1 solar mass. And 1 astronomical unit away is the Earth, right smack dab in the middle of the habitable zone. Mercury and Venus are too close. Mars, Jupiter, Saturn, Uranus, and Neptune are too far away to be in the habitable zone. Other stars, and I talked about these are called red dwarfs, small stars. Their habitable zone will be closer to them. The star between red dwarf and us would have its habitable zone a little further away. And then the massive stars would have their habitable zone even further away. So the high temperature of the inner solar system would have prevented any water or ices from being a part of the terrestrial planets. Planetesimals, the water and ice and atmospheres present with these planets was provided by those icy planetesimals that were flung into the inner solar system by the Jovian planets. And there's your answer to the atmosphere. Kuiper belt, the model predicts that some of the icy planetesimals would have been left out in the region beyond Neptune. We now know that as the Kuiper belt. And we have over 1,100 such planetesimals with diameters ranging between 30 miles and 1,200 miles known to exist there now. Pluto is one of these objects. I always tell students, if you're really upset about losing Pluto as a planet, you really want to memorize over 1,000 more planet things. So let Pluto go. It's really a Kuiper belt object. It's not really a planet. By the way, when my grandson was in first grade, I was invited to explain to these kids why Pluto is no longer a planet. I produced a PowerPoint for the benefit of the little kiddies. The theory explains several characteristics of the solar system structure. So that's evidence that it's a pretty good theory. It also is flexible enough to explain the peculiarities that I talked about. And there's evidence that this is happening in other places in our galaxy. I want to take a look now at where is that evidence outside of our solar system, or solar systems in the process of forming now. One of the best places to look is in.
Are they in that process now? Are they in the process? We're seeing that process now, because they would be hundreds of millions of light years away or something, right? Or some of them.
Yes, thank you.
We're seeing them now.
We're seeing them now as they were,
How many light years?
however light years away they are. So in the Orion Nebula, now Orion, people think because I taught astronomy that I can go out at night and tell you this star's name and that star's name, this constellation. I can't do that. I have no interest in that. I call myself an academic astronomer. I like to talk about astronomy, but I don't care about going out and getting cold. But one of the few constellations that I can identify is the Orion constellation. I'm sure most of you can too. It's a winter constellation, and it has 3 big stars in a row that make the belt of Orion the Hunter. Betelgeuse is a red giant star up in his shoulder, and I think that's Aldebaran is a blue giant. But the interesting thing is here in his sword are 3 stars. They're more faint than the stars of the belt, but you can see 3 stars there. What most people don't know is the middle one is actually a nebula. It's not just, and by the way, these are not on the plane of a sphere. All these stars can be millions and millions of miles away from each other. It's just that along the line of sight. So this one here is a nebula, or a cloud of gas. And within this nebula, if you look at it in a telescope, you will see several bright stars. But you will also see regions where stars are beginning to form. And these little blobs are regions where a stellar system is in the process of forming, where the gases of that nebula are beginning to condense into a planetary nebula. That's a bad word. Sorry, that's not the right word for that. And so here are 4 of them that you can see that are enhanced in this picture. By the way, these things were pretty much taken out of the textbook I used to use when I taught here at the college and taught astronomy. So they're pretty good. But you can see that there's 4 of them that show condensation clouds. And you can see the one in the upper right, you can see it's like a disk that you're seeing edge on. But this one here is more recent. This one was observed by the James Webb Telescope, and I just got this off of the internet. Decided I wanted to get more data, and I Googled, got this one, which is very clearly showing a condensation disk with starting to form rings, which will eventually, those rings will become planets. And as Mark points out, maybe they already are.
They were looking at us. They were looking at us in a telescope. They might be seeing our beginnings from somewhere in space.
Right. And this one is also a recent one that I got off the internet. And you can see there are actually 2 planets that have already formed in this one, as well as a condensation disk that will still be forming other ones. This is around the newly forming star, which has the interesting name of WISPI T2. So there is evidence, and there are planets outside of our solar system. We call them exoplanets. And again, I did a little current research to find out that on January 15th of this year, there were 6,080 confirmed planets and 4,532 planetary systems. That is to say, there's 4,532 stars. Some have more than one known planet orbiting them. Most of these exoplanets, though, are very massive, more like Jupiter's mass. It's a lot easier to detect the more massive ones, obviously. And they're not often detected by seeing them. They're detected by what happens to them, what happens as they pass in front of their star, and the star goes dimmer. Or they're detected by how their spectrum will vary. So if we were looking at the planet going around oh, that's binary stars. Forget that. But you can also get a spectrum from them, and you can see the shift in the spectral lines as they're moving toward or away from you. Their orbits are generally much smaller. That makes them more easy to observe too. The orbits are much smaller. And so they're large, Jupiter size, and they're hot. And so they call them hot Jupiters. And their orbits are generally highly eccentric. They're not very circular. They're more extremely elliptical. So that's mostly what we find. Now we are finding Earth-like planets now. If you pay attention to these things, you will see that we are finding planets that possibly could be in the habitable zone and could host life. By the way, I was simply a teacher of astronomy. I'm not a researcher. I don't need government grants. But if you want a government grant, you have a project that may find life somewhere in the universe. That's important to some people. We'll talk about that. I believe I'm going to have time. Yeah, I'm going to have lots of time, I think. Now, the Earth's moon, very important. It's unique in the solar system, and it is important for us to have life here on Earth. Shirley, you have any questions yet?
Yes. So what does the moon do to make life on Earth?
Anyway, again, I invite you to ask questions as things come to you. Like, why is the moon important for life on Earth? It's relatively large compared to the planet that it's orbiting. Now, it's not the biggest moon in our solar system. Jupiter and Saturn have bigger moons than our moon, but they're orbiting a much bigger planet.
Jupiter had almost Earth size moon or something. I thought it was almost Earth size.
Yeah, Titan is the biggest one, and I don't know, it's somewhere between the moon and the Earth size. But our moon is relatively large compared to the planet that it's orbiting, which makes it a pretty good shield, for one thing. Its large size and distance from the Earth also make total solar eclipses possible. Now you say, what is that important? When you look at the moon and the sun in the sky, they occupy about the same circle, same size circle. So our moon, in certain, okay, the moon's orbit is not circular. The Earth's orbit around the sun is not circular. So the distances between us and the moon and us and the sun vary, but there are times when the distances are just right so that the moon just covers the sun, which enables us to do what? See what? Louder?
A lot more stars right around the sun.
Well, you can do that.
See the corona?
You can see the corona, the outer atmosphere of the sun, and you can see the inner atmosphere of the sun. And you can see activity on the surface of the sun with prominences moving above it. But one extremely important thing is that you can see stars that are behind the sun.
Like bending around them.
Because of general relativity says that that light coming from that star, which would go past the sun and miss us completely, is bent by the sun's gravity and comes to us. Which was a very important confirmation of Einstein's general theory of relativity. But anyway, eclipses are possible here, which wouldn't be possible on other planets. And the tidal effects of our moon are extremely important to sustaining life. Without the tides, the ocean would not be able to replenish and cleanse and refurbish. So the tidal effects of the moon are very important. By the way, can anybody tell me why there are 2 tides a year, 2 tides a day? What's the moon? How does the moon produce tides? It's gravity. It pulls on the earth and the earth's water. And the closer, the near side of the earth's water is pulled more strongly towards the moon. And then the earth is pulled more strongly towards the moon than the water on the far side. So you have 2 bulges, and the earth rotates under those 2 bulges, and that's why you get 2 highs and 2 lows here. Now, my wife and I took a trip with her mother. Yes, it was all. And to the Bay of Fundy. Have any of you been to the Bay of Fundy? Yeah, it's fundamentally Fundy. The tides vary there by as much as 50 feet from high tide to low tide. And we made sure we were there. The most extreme tides occur at new moon and full moon, when the sun and the moon are working together. And we were sure to be there at the highest high tides, lowest low tides. It was pretty extreme.
It's really sad. Like you could be, well, Mom and I were ourselves, we were standing kind of on a bridge or something. And there was an inlet where the boats would park and then they could get out to the ocean. And the boats were going lower and lower and lower, and they were sitting on the gravel. And then when the tide came back in, they go back up. So if you want to get in or out of there, you have to time it just right. And all of a sudden, there would be all these boats coming out. And as that tide went down, there was a huge dead tree underneath. And then it started coming back in. It got buried by water again.
There's on the New Brunswick side of the bay, there is the city of St. John's, and the St. John's River flows into the bay at low tide and out of the bay at high tide. There's a place there called Reversing Falls. Well, it's not exactly I wanted to see a falls go both ways, but that didn't. It's a rapids. But because of that, there's only a certain time of the day when that is navigable, and the boats that want to come down the river into the bay, or vice versa, have to be there at just the right time. But we sat there for the whole day, and
What makes that the highest tide?
pardon, what makes it?
Yeah, why?
Yeah, it's the shape of the bay. Yeah, they explain it like it's like a bathtub with the water sloshing back and forth in the bay. It's the shape of the bay that causes that. Good question. Most of the highest, most extreme tides, as I understand it, anywhere in the world. and maybe the orientation of the bay as well. But they have, I think they actually have their energy producing systems that take advantage of the flow of the tide in and out. It's quite extreme and quite interesting.
So the gravity is not greater there than in other places, it's just the lay of the land.
Right, right. Shape of the land and orientation. Also, the gravity of the moon stabilizes the rotation axis of the Earth. It's very important that our rotation axis be roughly at 23.5 degrees. And it's stable. Now, it does vary slightly between 23 and 24. But it's pretty stable. By the way, did you know that, of course, the north axis points towards what star? Polaris, or the North Star. Now it points there. There's a 26,000 year period where precesses around. So in 13,000 years, it'll be pointing at a different star over here. But again, not something you need to worry about in your lifetime. And as I mentioned before, it partially protects the Earth from being struck by meteors. So our moon is, not only is the Earth in just the right place, around just the right star, but it's got just the right moon. The explanation of how we got our moon has an interesting history. There are basically three possibilities, only one of which makes sense, we've discovered. And this is the one, it's called the collision theory, I guess, name for it. A Mars-sized body early in the solar system, when these things are all flying around. It's called Theia, but of course, Theia is long gone. It collided with the Earth about 4.5 billion years ago, struck it, and the two then were blasted, both of them, and material from both of them settled into the remaining Earth, and also some of it went out or beyond, but the gravity kept it in orbit. And over time, the particles that were blasted away formed into the moon. Also, that's probably what caused our axis to be tilted 23.5 degrees instead of being straight up and down, or at 9 degrees. So this is the theory that works because the compositions of the Earth and the moon are a lot alike. They're not exactly alike. If the moon had formed somewhere else and been captured by the Earth's gravity as it wandered by, it would not be the same composition, or nearly the same composition. If it had co-formed from the same material, it would have been exactly the same composition, but it's not the same, exactly the same composition. So this is the theory that we have come up with now as to how we got our moon.
Is it possible to speculate about where it struck the Earth?
Yes, but I wouldn't do it if I were you. I don't. It's possible to speculate about anything, but I don't think they have a clue as to exactly where that happened. Yeah, because the whole thing became basically amorphous, or it was all melted and then it reformed. So the crater would not be there anymore. Oh, that's the end of my slides. Okay, any questions about the formation of the solar system?
South cloud specific spaces. You're saying that the rocky planets was formed on the cold spring because of the, but then later you said that the what we're seeing exoplanets, we're seeing gas giants that are more or less in that same area of the sort of things. If I understood that right.
We're seeing planetary systems forming. The exoplanets are already formed in another planetary system
Those planets move out later on.
from their
As
stars.
they age into the solar system.
Are our planets moving further away from the sun? I don't think so. So I think they'll stay in their orbits.
So there's not a difference. There are lots, so they're not, so there may be smaller planets. Sure, in orbit to those things that we just can't see because.
Yes, there could be smaller planets beyond the tech. I mean, yeah, there's probably a whole lot more exoplanets than we know about. We know about a lot of them. I mean, when I first started teaching, we didn't know about any of them.
So is there an argument that because you have basically an infinite number of stars and therefore an infinite number of planets around stars, therefore basically an infinite number of possible Earths, that there got to be others out there?
Well, yes, Carl Sagan didn't say infinite. He said billions and billions of stars. There's got to be billions and billions of planets, and we can't be alone. Yeah, the key is the difference between billions and infinite. And I'm going to talk about that next. If God created this planet and us, he certainly could have created other planets and didn't C.S. Lewis write the space trilogy? There's at least 2 other planets that had life on them. And
We know where.
yeah, I remember a good friend who actually is the reason why I started teaching astronomy, because he shouldn't have been teaching it. He was. He said, you know, if there is life elsewhere in the universe, our issue is, do they know Jesus? But you know, how will we witness to them? You know,
Should we? Maybe they never went through the fall.
Carol Amber.
Make the same mistake twice. Maybe we'd be so inverted.
Something that Jose asked last week that I failed to finish talking about. And I have this presentation, which is shorter. And it has some cute stuff in it, but at any rate, we want to talk about the fact that the universe is anthropic. What does that mean to say the universe is anthropic?
Good for human life.
Anthro, human. And the universe is extremely fine-tuned to allow for us to be here discussing this remarkable coincidence. If the universe wasn't finely tuned, we wouldn't be here. Scientists have been discussing an ever-increasing number of physical parameters of the universe that have to be extremely narrowly defined in order for the universe to have any place that would be habitable or hospitable to play. It's a growing number of parameters, some of which are beyond the scope of this class. And I'm not going to enumerate them. I will refer you to, before I go any further, I'm not a geologist. I'm not an astronomer. But I have taught a lot of astronomy. And when I came to Montreat College, I was supposed to teach physics and physical science, of which physical science also contained geology and meteorology, of which I knew nothing. One of my predecessors was more of a geologist than a physicist. And he had lots of rocks and minerals. And I thought, well, let me see, I'll take a field book and see if I can figure out which these rocks and minerals are. So I made my best guess. Then I found there's a place in Nashville I could take them to where they're real geologists, and I got about a 50%. But I referred to this book before, written by Davis Young. First name is good. Called Christianity and the Age of the Universe. And that was published in the 80s or 90s. And he got together with he was a geologist in college. After he retired, became emeritus professor, he got together with this guy, Ralph Sterling, who was a geology professor now at Calvin College. And you can see how it expanded from this to this. This one says the Bible, Rocks and Time, Geological Evidence for the Age of the Earth. So if you, and I'm saying what we think scientifically is the Earth is not 10,000 years old, it's 4.5 billion years old. Big difference. And here's a Christian, who's a geologist, who will explain to you what the geology says about the age of the Earth. Leave it at that. And then I have a handout. And by the way, for you folks who are out there in TV land, if you would like to have a copy of the handout, here's my email. Send me an email, and I will attempt to send to you what's coming out to the rest of the class. And that's not the one you're going to get right now.
And that's an L in front.
That's the L. I didn't want to make it look like a 1.
Looks like an ichthus stand.
Well, it's a fish on its tail. So, I'll just ask you to pass some of these around.
Backwards.
And
He's showing his name.
this is an argument I just discovered because I wanted to get an update on the number of parameters. And so this is what I'm referring to now that's being handed out. Jay Richards of the Discovery Institute lists 21 of these finely tuned parameters. Only 21.
It was like 100.
Ross cites 128, or did his book that I was using at one time, but some are possibly dependent on others or combinations of others. And in this picture that I handed out to you, there is an explanation of why it should not be more than 21. Because the others are possibly combinations of the other ones. So, but the point is, when Ross does his calculations, he comes out with the probability of life in the universe that leads him to conclude that we are alone. If you just take the probability, 1 chance in 10 to the 60th or whatever of this, and 1 chance in 10 to the 120th of that, if you take all those probabilities and put them together, even with billions and billions of stars and planets, there's very little probability that life just gets here. But again, if God wants to make life somewhere else, he can. I don't know whether I want to follow Ross in that or not, but I am very skeptical about all these claims of UFOs. But I'm going to give you some quotes along the way here too. This is Paul Davies, who, as far as I know, is not a Christian. He's a physicist. In his book, The Mind of God, he says, suffice it to say that if we could play God and select values of these quantities at whim by twiddling a set of knobs, we would find that almost all knob settings would render the universe uninhabitable. In some cases, it seems as if the different knobs have to be fine-tuned to enormous precision if the universe is to be such that life will flourish.
They need to be set in the same, like,
They all need to be set with the same precision.
but also.
They affect us. Yeah, they affect you.
Thank you. So essentially, every science today does acknowledge the reality of fine-tuning, but there are varieties of interpretations regarding its significance. These various responses appear to be more a matter of worldview, though, than of science. And here are some anthropic principles. The weak anthropic principle, or WAP, says our presence in the universe necessarily imposes certain constraints of consistency, which require the universe to be compatible with our existence. That's definitely a weak anthropic principle. Then there's the moderate anthropic principle. The contingent fruitfulness of the universe is a fact of interest, calling for an explanation. And then there's the SAP, strong anthropic principle. The universe must be such that the observers arise within it, or nature must take on those characteristics to admit somewhere, sometime, the existence of conscious beings. Strong anthropic principle. Now, from this point on, the formulation of the principle moves beyond science and reason into the realm of teleological truth, but of a theological rather than a scientific character. So then there's the participatory anthropic principle, or PAP. Conscious observers are necessary to bring the universe into existence, and the universe is necessary to bring observers into existence. Or the universe wouldn't be here if we were not here to observe it. Participate in the reason for why the universe is here and we're in it. And then the final anthropic principle, or fact, you're going to love this one. The life that exists, past, present, future, will continue to evolve with the inanimate resources of the universe until it all reaches a state called the omega point. This omega point is said to be an entity that has the properties of a creator that can create in the past. The creator does not yet exist, but we, all life and all inanimate structures in the universe, are gradually evolving into God.
Where did they get that?
Now, one of my fellow Christians who is an astrophysicist calls this a completely ridiculous anthropic.
Crap.
All right, well, that's just a little, if you didn't catch all that, or the principles didn't make sense to you, don't worry about it. But what are the possible explanations of such a universe as ours so that it's right for us? Well, there is the God hypothesis. God has designed the universe for our existence, and it really takes a big old universe for everything to be right. This is a reversal of the Copernican principle, which basically said we're not at the center of the universe. Though we may not be in any special place in the universe, we are special in the eyes of the Creator, who went to such extremes to make a universe where we could ultimately become inhabitants. So, the universe is finely tuned from this perspective by God so that it can contain His creatures, us.
The rest is for the beauty that He created for us. The stars, the tides.
Well, that's not just beauty. Those things are necessary too.
Necessary, but I mean, it gives value to life.
First of all, how old did I say the universe was 2 weeks ago?
14 billion years.
About 13.787, I think is what we got narrowed down to. Billion years. And how old did I say the Earth is?
4.
And our star, the sun, is about 4.5 or 5 billion years. And where did the heavy elements come from? What was created in the beginning of the universe? What elements?
Helium.
Hydrogen and helium, and a little bit of lithium. So where did all the heavy elements come from?
Hydrogen. It started with hydrogen and helium.
Stars. The lighter elements were fused together by fusion in the cores of the stars. The stars blew up, spread those things out into space. Some of those heavy elements were only formed as a result of the explosion itself, and so on. So our star and our solar system are at least a second and maybe even a third generation in order to have the elements necessary for a planet with rock and mineral and metals to exist. So those stars out there are the reason why we are stardust. I used to ask my students, though, are we merely stardust? We are stardust if this theory of the origin of the universe and the solar system is correct. We are the result of stars that have blown up and sent their materials into space, which later condensed into our solar system. But are we merely stardust? There's a difference between being stardust and are being made of stardust. And that's all we are, stardust. More than that. Depending upon your worldview, of course. And I think everybody here has a pretty similar worldview. John Polkinghorne, a brilliant particle physicist in England, who traded his lab coat for a collar and became a priest. He says, there is indeed a meta question arising from the anthropic principle, considerations to which theism provides a persuasive, but not logically coercive answer. Theology, theism provides a persuasive, but from logically, you cannot coerce someone into it. Then there's the multiverse hypothesis. And this is what Jose was asking about 2 weeks ago, and I didn't answer him completely, or hardly at all. There's not just one universe, but a multitude of them, a multiverse. There's no way up. And by the way, we're in the lucky one. For all the dials are doing just right. All the others got the dials. At least one dial was off, and life could not form. But we're in the lucky one. Now, there's no way of falsifying this hypothesis any more than there is a way of falsifying God. So why would you choose that? You don't want to face a God to whom you might be accountable. On my sabbatical in 1999, my wife and I followed the Lewis and Clark Trail out to the Pacific Northwest. And we wanted to be on the Missouri River, I guess it was. And we found that we could rent space on this huge canoe. Not one that we were just the two of us responsible for, fortunately. Of course, the Missouri River was pretty well tamed. And so we go to meet this huge canoe, and it's Marianne and I, an old gentleman and his wife and daughter, And that was it for this canoe that would normally handle about 20 people. But you see, we were there in the off season when Mark was in school. I wasn't, because I was on sabbatical. Turns out this old gentleman was a physics professor who preferred the multiverse to a created universe. So I didn't debate him. I would have lost. He's probably smarter than me. But there's no way of falsifying either one of these. You choose based upon your perspective. Now, I am finding articles now that some interpretations of quantum mechanics, quantum theory, do allow for the possibility that many universes would have. There could be many universes. However, there's no way to experience any of them. The only universe we can experience is the one we're in. So, point number 2 there. And here's Paul Davies again, in The Mind of God. The many universes theory can at best explain only a limited range of features, and then only if one appends some metaphysical assumptions that seem no less extravagant than design. Occam's razor compels me to put my money on design. As always, in matters of metaphysics, the decision is largely a matter of taste rather than scientific judgment. And then Edward Harrison in Masks of the Universe says, here is the cosmological proof of the existence of God, the design argument of Paley. Paley's design argument was if you were walking along and you picked up a rock, you would have every reason to believe that there is a natural reason for that rock to be there. But if you were walking around along and you picked up a watch, you would think that somebody dropped their watch, that this watch was designed and produced by somebody. And so the universe has that appearance of being designed. Therefore, you would expect there to be a designer, as there would be a watchmaker. But Paley's argument, updated and refurbished, by the way, Mark, do you have anything to say about Paley's argument? I understand the philosophers are not thrilled with it.
Yeah.
We don't have it words or less. Okay, thank you. But Paley's argument is, yeah. So take your choice, blind chance that requires multitudes of universes or design that requires only one. Many scientists, when admitting their views, incline toward the teleological or design argument. Now, I don't know anything about Edward Harrison, but this quote seems like he's a believer. And my next slide is blank, so I'm done with that.
Lloyd, is the need for multiverse, is there a need for, multitude of universes simply because, okay, so the probability of us having life in this universe is small, so there must have been others to make that probability higher?
Yes, that's exactly it. The argument is, rather than accept that someone designed this universe perfectly so that we could be here, there are many universes. The probability of having one of those with all the dials set right isn't so bad because there's a lot of them. And we're in the lucky one. And so it's driven primarily by not wanting to accept a religious explanation, but trying to come up with what seems like a more naturalistic explanation. But like I say, it's not any more scientific than a design.
The theorists that hold this think there need to be as many universes as the possibilities. So 10 to the
Gazillion.
120 or something.
Yeah.
That's how many there, see, like, beyond our ability to count, that's how many there need to be. But again, it's not classifiable, so it's not a scientific theory. It's just like the God hypothesis has the same weight scientifically, because neither one are scientific theories.
Yeah.
That's the point. And if we had time, I mean, the problem with the philosophers' arguments.
Well, I have time for something I want to.
Okay, good.
This is I was, again, Googling, the parameters, and I came up, and this is a little video. It's only 6 minutes, a little over 6 minutes long. It does a real nice job of making the illustration for us. So I would like to show you that in conclusion tonight. And it's from this Discovery Institute. They are ID, intelligent design people. And
Yeah, let's see some stars.
David, I have an observation. Let's say that there is another planet with people, sentience, conscious beings.
you were somewhere.
You mentioned you like Paralandra, C.S. Lewis, imaginary planet. Do you think that the people in that planet would have committed the same sin that Adam and Eve did? And thus they will require the presence of Jesus coming to them for their salvation also.
And for you all out there, that's Jose.
Yeah, I was trying to ask the question, because you're going to get asked again. I'm going to turn it up a little here.
You want me to ask you the same question again?
Yeah, that's something, but we can hear you loud.
Okay. So you mentioned the very slight possibility of other planets being in the Goldilocks section and maybe containing conscious sentience beings. I mentioned the Paralandra and the C.S. Lewis's book. Do you think that the beings there would have committed the same sin that Adam and Eve committed, and then they would require a Savior, Jesus Christ, to come to them like he had to with us?
Yeah, well, of course, if they didn't commit sin, then they wouldn't have needed Jesus. And according to C.S. Lewis, there's a 50-50 chance that they hadn't. Because on Paralandra, didn't, but on
On the silent planet.
that Earth.
That's Earth, yeah. Yes.
But well, I guess 2 out of 3 failed. So yeah, that's an interesting theological question. What do we do if we encounter other life forms from other planets?
Yeah.
But according to the probabilities, at least a lot of us think that's not much chance.
No.
But God could do anything he wants, can't he?
No, they would be millions and millions of light years away from us. So I don't think we'll ever get to meet any of them.
Unless they have a better technology than we do, which of course that's what everybody assumes. They have better technology than we do. They're more advanced. But anyway, thank you, Jose.
I thought that would be, they need another Jesus Christ to come to them.
Mike? Yeah, I would think so, most likely. Larry Norman?
If there were people on other planets, Jesus has gone and died for their sins too.
He has? Okay. Well, only if they're elected. Only if they're elected. Okay, I'm done, and I do have another handout next week. And by the way, all of you out there in TV land, that's ldavis@montreat.edu if you want to get these without actually showing up here. Oh. Yeah, you can pick them up. That's what I'll do. I'll just lay them here and you can pick them up. But next week is the history of the debate. And Dr. Ben Brandenburg from our history department college will be giving his standard lecture on the history of the debate. This is something that I produced out of a book called The Creationists by Ronald Numbers. History of the Creationist movement.